So before we get into your notes today, we're going to just very quickly go over the warm-up to make sure you have the correct answers because we are preparing for the test that's coming up next week. Question 1, the most and least reactive groups on the periodic table. Here are the groups that we learned about a couple of months ago. The most reactive group on the periodic table is group number 1, the alkali metal group. The least reactive group on the periodic table is group number 18, the noble gases. If you also remember, group 17, the halogens, is a very reactive group, but it's a non-metal group. Group 17, if you remember, likes to bond with group number 1 because everything in group number 1 has 1 valence electron, and group 17 has 7 valence electrons, and together they make a full valence shell. Question number 2, compare the properties of the elements to the properties of the compound they make. Well, if you remember all the way back to the iron sulfide demonstration, I took iron, this magnetic grayish metal, with sulfur, a non-metal, solid, really stinky substance, and I heated them up to create the compound iron sulfide, which had completely different properties. So here's the answer. The properties of the compound are totally different than the properties of the individual elements, because a chemical reaction has taken place. As we go through our notes today, I want you to be thinking about what you wrote for question number 3, because as we go through our notes and I give you the answer to this, you may have to come back to your warm-up and fix it depending on what answer you put. So here's what we're going to do today. We're going to start on IP56. I want you to title it. We're going to be talking about speed time graphs today, also known as velocity time graphs. So I just want you to know that these two terms can be used interchangeably because you may see either one of these titles at different times. When you make your graph on your page, I want you to make a large Y and a large X axis, and then label these intervals. I'm not going to be super picky about how big your graph is or how far apart your intervals are, as long as you have labeled your X and Y axis correctly. And this is the only thing you're going to put on IP56, so you can make it pretty big. In order to take some notes on a speed time graph, let's go back to this animation that I showed you the other day. I'm going to show you a car going slow and then speeding up. Notice that the velocity time graph, the line goes up as the car goes up because it's showing that speed is increasing. So on your graph on page 56, make an upward sloped line. Now, if the car's speed is increasing, it was going 0 miles an hour, it was stopped at first, then it was accelerating to 10 miles an hour, 20 miles an hour, 30 miles an hour. It was accelerating by speeding up, and we know that that is called a positive acceleration. It is accelerating because it's speeding up. If I make the car travel at a constant speed, it's not speeding up, it's not slowing down, that line on the velocity time graph is completely flat because it's showing that the speed is not going up, the speed's not going down, the speed is staying the same. That's different than a flat line on a distance time graph or a constant speed line on a distance time graph. So on your notes, please make a flat line. A flat line on a speed time graph means 0 acceleration. It is moving, but it's not accelerating. It's traveling at a constant speed. If I make the car start fast, sorry, I'm going to do that again. Let's say I start the car fast and I slow it down. Notice that the velocity time graph line is going down because the speed is going down. We know that slowing down is part of acceleration, but it's negative acceleration. Make a downward slope line on your graph and label. And watch the difference now when I stop the car on a velocity time graph versus a distance time graph. On a velocity time graph, if I make the speed 0, look where the line is. It's all the way down on the x-axis because it's showing that the speed is 0. Speed went all the way down. The car stopped, speed is 0. That's different than if the car just stopped in the middle of the road and it stayed in the same spot for a distance time graph. So on a speed time graph, make your line go all the way down to 0 and then across on your x-axis, showing that the speed is actually 0. Once you've taken these notes, now you're going to work on OP 56. On OP 56, I'm sorry if my camera is in the way, but each line or each quadrant on OP 56, you're going to do this. Title it Comparing Distance Time and Speed Time Graphs. Then label each quadrant. Quadrant 1 will be labeled stopped, quadrant 2 constant speed. Quadrant 1 will be labeled stopped, quadrant 2 constant speed, quadrant 3 speeding up, and quadrant 4 slowing down. In each quadrant, you're going to make basically like a big L and label it. You're going to make 2 of those in each quadrant. So DT standing for distance time graph, ST standing for speed time graph, DT, ST, distance time, speed time, and then in your last one, distance time, speed time, and the exact same thing. Here's what you're going to do. You're going to use a different color and show me on this graph what would the line look like on a distance time graph if the object was stopped. But what would that line look like on a speed time graph? In this quadrant, what would the line look like in a different color? If the car was traveling at a constant speed, what does that look like on a distance time graph? What does that look like on a speed time graph? If the car is speeding up, what would that line look like on this graph versus this graph? If the object is slowing down, what does the line look like on a distance versus a speed time graph? Then not only are you going to show me, you're going to tell me. Once you show me, write it in a sentence. On a distance time graph, stopped is a, what does that line look like? On a speed time graph, stopped is a, what does that line look like? And do that for every single graph.